right, good morning. So the rain has scared some people off, but that won't stop us in our journey towards file systems. So we finally get the last piece of the puzzle for the course. Aside from the last thing we'll look at is virtual machines, which gets into fun page table stuff. So if you thought multi-level page tables were fun, well, with virtual machines, there is now nested page tables. But that's a topic for a later lecture. We'll probably spend this lecture and the next one on file systems. So file system, you're probably used to this right now. A normal POSIX file system looks something like this. So this layout of folders is actually a standard called the FHS, which is the file system hierarchy standard. So according to the standard, you have to have a special root directory. So that starts with a slash. And then within that directory are some defined other directories that must be there, like bin, dev, etc, home, and mount. And then within those, you can create whatever files you want. So the normal thing you do is in the home directory, each user gets its own directory within that they should only be able to read and write to, which is what's kind of on the UG machines. And then usually when you use the file system or when you use your shell, you have a working directory. So there's a directory you're currently considered in and working from. So if I'm currently in the directory home and John, there's two different paths we can have. There's an absolute path and a relative path. So a relative path would be relative from where I currently am, and an absolute path would be starting with root. So if there's todo.txt and I want to take a relative path to that, well, todo.txt is in my John folder, and that's currently where I am. So the relative path would be just maybe /todo.txt or maybe just todo.txt by itself. Then the absolute path would be starting from root, so it would be /home/john/todo.txt. And then for USB, if I did a relative directory for USB, well, I have to, if I'm in John, I have to do .. which would take me to home, then another .. which would take me to root, and then /mount/USB. Or if I just did the absolute path to USB, it would be /mount/USB. So that's kind of what we're all used to, and we'll see in later ones that the dot and .. are actually entries in the in your file system. So there's kind of special file names, and the only thing that's special about them is their name and how someone defined to use them. So within all the directories, there will actually be an entry called dot, which is supposed to refer to the current directory that this represents. And then .. is the parent directory. And then the tilde, the little squiggly line, is the user's home directory, which is usually also an environment variable called home. And then relative paths are always going to be calculated from the current working directory, which may just be set with an environment variable like pwd. So fun fact, does everyone kind of know on Linux, or at least the UG machines, that if you start a file with a dot, that's like a hidden file? So that was actually kind of a bug that became a feature. So when someone wrote ls, well, they didn't want to show dot and .. because those are defined ones. You don't really care about seeing them. So if you were to display all the files to a user, well, I would want to ignore dot and .. Well, if you're a very clever programmer, you'll be like, well, those are two special cases. I can generalize it. So both of those start with a dot. So that programmer just wrote that, hey, if it starts with a dot, don't show it, thinking that it would only cover dot and .. and no one would actually make files that start with a dot. But then, of course, someone made files that started with a dot, and then they couldn't see them. And that's just how it became. So now, if you just start a file with a dot, it's understood that that should be a hidden folder, but it all stemmed from one programmer trying to be really efficient and handle both those cases at once. So that is the fun fact about how hidden files came about. So for accessing the content in the files, well, you can access files sequentially or randomly. So if you just open a file like what you've been doing and you read from it, you're reading everything sequentially. So each time you call read, it would advance the position in a file. So the next time you call read, you continue reading from where you left off. And then if you write to the file, you could be doing the same thing where writes just happen from where you left off, but you might start writing from the end of the file instead of writing to the beginning of the file. Otherwise, you might be creating a new file in that case. Then another way to access files is just like randomly. So you might just want to randomly jump all over a file and read and write in any order. And for that, you would have to specify a position required for each operation, which we don't actually know how to do yet, because so far, unless someone is doing something really tricky, everyone has just been accessing files sequentially. So they just open them, they read and wrote. So the first call we're all familiar with, that is the open system call that takes a path name, some flags, and then a mode. So in this, by default, you just get the position that starts at the beginning of the file. So if you read from it, you read starting at the beginning of the file and it updates the position. And if you write to it, it would start writing at the beginning of the file, maybe overwrite some stuff. So usually if you're writing to the end of the file and you want to just throw that information at the end, one of the flags you can give is this append flag, and that would just make that position point to the end of the file. So any write system calls you do will not overwrite anything. It will just go directly to the end of the file. So the second system call is the lseek, which is the system call you use to actually change that position so you can actually randomly access files. So lseek will take a file descriptor and an offset, which is just a number to change the position to. And what that change represents depends on what that third parameter is that went. So it can take one of set seek, cur, or end, and cur is just short for current. So if that whence is seek set, then that means that offset is absolute. So if you choose seek set and their offset is 0, it's always going to go to the beginning of the file. If you set seek set and then have your offset at 100, it's always going to go the 100th byte. Then the cur, which is just current, and end is relative to where the position currently is and relative to where the current end of the file is. So what you could do is if you want to just advance, say 100 bytes, you would set once to seek current and then your offset to 100, and that would jump 100 bytes from where that position currently is. So if you just want to skip 100 bytes in the file or however long. Or of course, this could be negative if you want to go back. And then seek end is just from the end of the file. So if you want to read the last byte of the file, so if you wanted to do that for whatever reason, you would set once to seek end and then offset to -1 or to 0 to read the last byte, -1 for the second last byte, and so on. So they're both relative, and so yeah, current and end are relative, and then set is absolute. And then you have an offset. So this will actually change the position where it will read and write to that file next. Everyone good with that, because it will get weird. So we saw this just for completeness that, we accessed it in lab 1. So you had open dir, read dir, and close dir. And you'll see the actual structure of this possibly in the next lecture. But it's just a special thing. You open it, and then you can call read dir over and over again until it returns null, and that will give you some type of directory entry. So just remember there's like a D name and stuff, and we'll see all of that directory entry pop up in the next lecture. But that's just so you know that it will probably come, and we can get reminded of it. So now we can talk about what's actually in the process control block for files. So every process has a process control block that stores things like its process ID, its scheduling information. If it since it can context switch, it would save, the registers from when it switches. It would have page tables associated with it. So we've learned a lot more about the process control block than what we started with in like lecture 4. So now we know a lot of what's in it, and the last thing we actually care about what's in it is that file table. So the file table is stored in the process control block, and it is just an index into this thing in the middle here, which we'll see later, but that name is the global open file table, and that is maintained by the kernel. So within a process, all your file descriptors just point to some entry in there. And every entry in this table has 3 things. It has a position, a flag, and a vnode. And a vnode is just a virtual node. It represents something that you can read and write to. So in this example, we have 2 processes, process 1 and process 2. In process 1, it's got 3 open file descriptors, but we'll only talk about the first 2. So the first file descriptor 0 could be pointing to this entry. And this entry would have a position, flags, and then have a vnode that points to some file, let's call A. And then its file descriptor 1 would point to something else that has its own position, flags, and a vnode that could be pointing to file B. And then in process 2, its file descriptor 0 could also have its own separate position, flags, and vnode, where that vnode points to the file B. So 2 vnodes can point to the file B, and in this case, both of these entries have an independent position, so they could both sequentially access the file, and both of those processes could read the entire file because they have their own independent position. So each time they read from it, they'd read from that file, but because they have their own independent position, they could actually read the whole file because they're not sharing anything. But there are cases where things will get shared, and that it will be a source of problems. So each process contains a file table in its process control block, and the file descriptor is simply just an index into that table. That's all it is. That's why it starts at 0, and that's why the numbers are so low. So each thing in the kind of local file table will just point to a system-wide global open file table, and that is maintained by a kernel. So that is also why fork, your file descriptors are all kind of shared, because even if you copy the local file table, well, you're just copying what it points to. So both the processes are pointing to the same thing, and that way they can share. So there's like a layer of indirection there. There's a reference. So the global open file table, or GOF, if you want to call it that, holds information about the seek position and flags, and then points to a vnode. Vnodes are just anything that needs to support a read and a write. So it could be an actual file. We know from Lab 4, it could also be a pipe, which is basically just a buffer. So a buffer is something you can read and write to. And then we saw with sockets, you can also read and write to sockets as well. So they can be, regular files, pipes, network sockets, or anything else you can read and write to. It's a really general thing. So again, remember what happens on a fork. So the process control block just gets copied on a fork. So specifically for us, the local open file table would get inherited completely. So they both have their own local file table, but at the beginning, after the fork, they're both copies of each other. So if you modify file descriptors in one process after the fork, it doesn't affect the other ones. Again, you should have gotten some practice with that in Lab 4. But they both point to the same global open file table. So this is what it would look like if, say, process 1 had a file open, had file A open. Well, whenever you open that file, it would create a new file descriptor for you that points at a new entry. So that new entry would have its position, flags, and vnode. And then whenever we fork, we would create a process. So let's call process 2 just the child process to make it easy, and process 1 the parent process. So when you fork, The child process is also going to have a local open file table where file descriptor 0 is going to point to the exact same thing. So now they are both sharing a position, which will lead to some interesting things if you are not careful about your file descriptors. So you could have a file, you could open a file in a process. So say you're opening like readme.txt or something like that. You fork, and then in both of the so what would happen if in both of the processes I call read? Yeah.
Like one would read and then set the position to the next read, and then the other might call read and read the next block.
Yeah, so there's because they're sharing the position, if both of them are trying to call read, both of them will not read the entire file. So there's a few scenarios that might happen because they're sharing this position, and the kernel is going to make sure everything's read safe and everything like that. So what could happen is one process reads the entirety of the file and then updates the position to the end of the file, and then if the other process tries to read it, it's going to get that end of file signal where read just returns 0. So one process might read the whole file, and the other process gets nothing, and it might also be switched and be the other way. Or if it's a really, really big file, what may happen is one process reads a chunk of it and then, updates the position, and then the other process reads another chunk of it. So one process will have one chunk of the file, the other process will have another chunk of the file, and they'll be mutually exclusive. So each one will only get like a bit of the file, and it will probably make no sense to them. So that's some of the gotchas for sharing. So since you fork and you're pointing at the same global open entry, that position is actually shared between processes. And that leads to very interesting things, especially when we have that seek system call before. So remember, the seek system call just updates the pointer. So because they're sharing the position, if you forked and then in one process you seek to the beginning of the file, well, that would also seek to the beginning of the file for the other process as well. So you could interfere with each other. It could just seek to the end, and then neither process reads any of the file. So you could get some very interesting things if you are sharing a file descriptor and another process decides to seek on you and do some interesting things because you're never going to figure it out. So the alternative to that, if you want to be independent, so you want to have your own position, is every time you call open, that creates a new entry in the global open file table. So you would want to perhaps just reopen the file or only open it after the fork instead of before the fork if you for sure did not want to share this position. So we can look at that in an example. So say we have something like this, where we have a parent process that goes through, it does open todo.txt, opens as read-only, and then there's a fork, and then after the fork, there's now two processes. So this is kind of review for processes, and then both of them open b.txt. So assuming there's no previously open files, not even the standard ones, how many file descriptors does the parent process have open? 2. And what files are they? Okay, yeah, todo and b.txt. What about the child process? How many files does it have open? 2 as well. todo.txt and b.txt. But how many global open file tables entries are there? 3, right? So if we have this, what was that? So if we have open todo.txt, whoops, fork, and then open b.txt. Well, in our original parent process, so we'll just call this process control block 1 parent. So if we assume no file descriptors are open, then, or no file descriptors are currently open, then open is going to just return the next unused one. So it would return file descriptor 0. And then an open will always create a new entry in the global open file table. So here is the global open file table. So it will have a position, some flags, and then a vnode. And that vnode is actually going to point to todo.txt. And file descriptor 0 is just going to point to this entry here. And then when we fork, that would create a new process, a new child process. So it would create a new process control block for the child. And it would copy the table, so the local open file table. So it would also have a file descriptor 0, which points to the exact same thing. So now they are sharing that same position. So if one read from 0, it would advance the position, then the other wouldn't read it, would start reading based off where it picked up from. Or if one of the processes did that seek system call, it would update the position, and then it would affect the other process. But because we have the openb.txt after the fork, both calls from the process are going to create an entry in the global open file table. And because they're processes, we're not sure which ones are going to run first. So let's just assume the parent runs first and creates an entry in the global open file table. So it would have a position, flags, and then a vnode. And that vnode would point to b.txt. So, and then the file descriptor that would be returned for that process would probably be file descriptor 1. So file descriptor 1 would point to that entry in the global open file table. And then the child would at some point execute and then do its open call, which would create a new entry in the global open file table. And it would have a position, flags, and then its own vnode that also points to that file. And then it would get file descriptor 1 that points to it. So each process has 2 entries in its local file tables. So there's 2 entries here, 2 entries in the child. And then in the global open file table, there's a total of 3 entries. So any questions about that? Okay. So there's 2 entries per process and then 3 entries in total. And here's again, so you have it on the slide so you don't have to write it down. Okay, so the next topic would be, hey, I need to store these files somehow. So we kind of saw that the structure of the disk devices are they give you a bunch of blocks that are kind of like pages. They may or may not be the exact same size as pages, but you can allocate them like pages. So if we want to store files, how should we store them? So one thing we could do is something called contiguous allocation, which might be the first thing everyone thinks of. So say in this example, we have a green file, a red file, and a blue file. Well, to keep track of where the files are, the green file, you could just say, hey, it starts at, say we'll call these big things of information just blocks. You can say, hey, it starts at block 0 and it's three blocks long. Then for the red one, hey, it starts at block 7, and it is 6 blocks long. And then same thing, same deal for the blue one. So would that be a good idea for files? Which, hint, this is kind of related to memory allocation. Yeah. Yeah, so wouldn't it lead to a lot of fragmentation? So that is the huge issue with this, because also unlike memory allocation where you just give some memory back and it just uses it, well, files can grow and files can shrink and files can get deleted. Well, memory can get deallocated, but files can grow and shrink kind of at will. So in this scenario, what would happen if I wanted to make the red file bigger? Yeah. Yeah, so I have a few options here. If I wanted to make the red one bigger, well, assuming this is all my blocks, I couldn't actually move the red one, because if I move it down, oh no, I could move it down. So I could move it after the blue one and then give it another block. Or I could move the blue one, which is probably smaller, and then give the red one another block. But I'm moving possibly a lot of information here, and there's no guarantee that it's going to get any better anytime soon. And the other option would be just, hey, your operating system can just be like, yeah, sorry, I can't do that. That's too bad. Which, if your operating system did that and you worked on your lab, you made your file bigger, and then you tried to save it and your kernel just said, yeah, sorry, can't do that, you probably wouldn't use it anymore. So probably a bad idea, especially we know that that fragmentation issue is going to be a very large issue, and we want to use our disk as efficiently as possible. So it's going to be fast, as long as there's no modifications and we can lay things out properly. And it's space efficient. If we need to keep track of the contents of a file, well, we just need to know what block it starts with and how many blocks it takes. And that's all we need to represent a file. And then we could just read a file by chasing down those. So if we want to access any block, you would know exactly what block you need to access by how big the block is and what byte you're accessing. So if I want to say my blocks in this case are the same length as a page, so they're 4 kilobytes. Well, if I have to access byte 100, it's going to be on the 0th block. And then if I want to access byte 5000, it'll be on the 2nd block. And I know I know exactly what block I need to go to by just what byte I'm accessing. So that's really fast as well. But you have the problem where files can't really grow that easily. There's going to be lots of external fragmentation when files are deleted or truncated. We might have these big gaps, and you probably don't want them, and we can do better for files. But in this case, you're going to see this pop up every time that for file systems, generally they only care about blocks, and files may not nicely fill a block, so there's always going to be some type of internal fragmentation because a file might not perfectly fit within a block and waste some information. So for all these, we're going to have some internal fragmentations as long as we just care about blocks, but our goal is to not have any external fragmentation. So if we don't want any external fragmentation, we can do the same idea that the Linux kernel has for just giving pages to processes and do something like a linked list of free pages. So this is called linked allocation. So unlike the kernel, where the kernel just has to keep one track of it and then allocate it as it's used, we would have to do something like that for every single file. So it might not be the most efficient, but this is one thing you could do that would actually work. So what I could do is within a block, so say all these green blocks represent that green file, all you would have to specify all you would have to specify to say where that file is you would specify the first block, and then within each block would have a pointer to the next block. So the blocks would be a little smaller in terms of usable size. So say they were sizes of pages again, so like 4,000 96 bytes. Well, if you wanted to store the pointer to the next block on the block, and the pointer is like 4 bytes, well, then you could actually use 4092 bytes for storage, and then the 4 bytes are for the pointer to the next block. So in this case, they would point all, and then once I hit the end of the file, that pointer would be null or something like that to indicate that there's no more blocks for this file. So it's a bit better. So we got rid of our external fragmentation using that and kind of recycled the idea we got from the Linux kernel. It's really space efficient because for every file, all you need to store is the first block, and then you can figure out what the rest of the blocks are from them. But that is also the drawback, where your random access is going to be really, really slow. So to traverse anything, well, I can't just go to block 5 of the file directly. I would have to start at the first block and then traverse all of it until I got to the block that I want to get to. And we know this is going to be even worse because let's assume they were just in memory and this was pages. Well, every time I access a pointer there, because everything's so far off and all the pointers are on different pages, it would be like having a TLB miss every single time. So even traversing it is going to be really, really, really slow. So what would I do if I wanted to speed up that traversal? So if I have to access it on different pages and that's slow, could I do something a bit better? Yeah. Hash map, so we can do it not being that fancy. So if all the pointers are stored on different blocks and I want everything to be closer together, where should I store all the pointers? Yeah, I could essentially store all the pointers in an array on like a single block itself. So that's what a file allocation table does. So all it does is move the pointer from the block itself to its own space, and then each array element represents a block, and it would have a pointer to it. So in this case, before I had block 0 point directly to block 6, and that pointer to block 6 was stored in block 0. But instead of doing that, I would store all of the pointers in just a big array. So if I access block 0, I could access its pointer directly and then just jump a few bytes. So it would point to 6. And then from 6, I could follow that to point to 2. And then from 2, it points to 13. 13 points to 9. 18. And then 9 points to 18, and then that's the end of the file. So it's the same idea as linked allocation. I'm just moving it to a separate table. So who here has formatted a disk before and saw on the options there's an option called FAT? Seen a few people? So this is FAT. So FAT is file allocation table, and that's exactly what this is. So FAT32 means that the pointers to blocks are 32 in size, 32 bits in size. So that's all it is. So each file would have its own file allocation table that essentially has a linked list of all of the blocks that are used. So this is a bit better than linked allocation. We again have no external fragmentation, still have internal, but we sped up our random access time by a lot because that file allocation table can be held in memory, and then we get all the advantages of our caches and everything like that. The big disadvantage is that the FAT size is linear to disk size, so every single file is going to have to be able to reference every single block in memory, and most of the time that file allocation table is going to be empty, minus the blocks that are actually used to do the allocation. But no matter what, every file is going to have to be able to reference every single block. So The file allocation table is related to how big the disk is. So the bigger the disk, the larger your file allocation table is, and the less room you have to actually store files. So this is still using the idea of a linked list. So what could we do if we wanted to do something even better than a linked list? So what is generally faster and easier than a linked list? A tree? What's simpler and faster? What, a stack? What about just an array? Array would be simple. Why am I storing the entire list of pointers for everything? Why don't I just store that for this file directly? Block 0 is block 1. Block 1 of this file is 6. Block 2 of this file is 2. Block 3 of this file is 13. Why don't I just store that directly in an array, and then I can just look it up directly. I don't need a hash table, I don't need a tree. Let's use a good old simple array. So that's exactly what indexed allocation is. It's like, screw this, why would I use a linked list and try and figure out what block is which? I'll just store which block is which. So indexed allocation is for each file, it would store just an array of what block represents what block of the file. So you would actually use a block to store the array, which steals an idea from our page tables, where we have a page table that fits on a page. Well, we store our indexed allocation map on a block. So this red block could store our array of pointers to blocks, and then we would just index them in the order that our file needs them. So if our file takes 6 blocks here, well, we just look them up directly. So block 0 would point to block 0 on the device. Block 1 of the file would point to block 6 on the device. And then block 2 of the file would point to block 2 on the device, etc. So that's going to be way faster. That's an array. We got all our nice random accesses. Everything is really, really fast. And we don't have such a problem anymore, because now this indexed array is only proportional to the size of the file, which makes sense. So we have to keep track of how many blocks represent the file, but it's not proportional to the size of the disk anymore. So we got rid of that weird dependency. So that's good. So for index allocation, we still have all our nice advantages. Our files can still grow and shrink at will. We still have no external fragmentation. Still have internal fragmentation, because that's the trade-off we use for these big devices. But now we have nice and fast random accesses. But now we have another disadvantage where, if we're using that trick of storing all of the pointers on a block, well, we have a limit. So with file allocation table, a file could span the entire drive if you wanted to. But now we're limited to the size that the number of pointers we can fit in that block. So let's take a look at that scenario. So if we assume we have a block that we used for indexes, so that block will just store pointers and that's it. So no other information whatsoever. We'll just make it simple, where it just stores pointers to blocks. Well, let's assume a block on our disk is 8 kilobytes in size, and then a pointer is 4 bytes. Well, this will look a lot like page tables, where we can kind of calculate the maximum size of a file that can be managed by a single block. So if our block size is 8 kilobytes, well, like page tables, powers of 2 are probably good. So what is 8 kilobytes in powers of 2? Yeah. 2 to the 13. So our block size is 2 to the 13, and then our pointer size was just 4 bytes. So what's 4 in powers of 2? 2 to the power of 2. So, knowing that, how many pointers could we fit on a block? Yeah. 2 to the 11. So that's how many pointers we could fit in a block, because 2 to the 11, well, that's the same as our block size divided by our pointer size. And since we know fun exponent math, that's just the same as 2 to the power of 13 minus 2, which is 2 to the 11. So I can fit 2 to the 11 pointers, and then each of these pointers points to a block. How big is a block? 2 to the 13. So what is my maximum file size? Yeah. 16 megabytes. Yeah, or if I'm not skipping steps, it is 2 to the 11, which is the number of pointers I have, times the size of our block. So it is 2 to the 13. So that's the size of our block. So that together is 2 to the 24. So if we want, we can rewrite that in megabytes. So 2 to the 20 is a megabyte. So it would be 2 to the 4 megabytes. And MBI, again, is the powers of 2 ones. The megabytes, if you just write it, it's like somewhat ambiguous depending on who you talk to. But MIB is definitely powers of 2. So this would be 16 megabytes. So if we do that, the maximum size of our file is 16 megabytes. Would anyone like to use that operating system? So maybe that was cool, you know, in the 70s or something like that, or possibly before that, but not gonna quite do it today. So that will be what we discuss in our next lecture. And hint, we'll probably borrow some ideas from page tables. So you thought page tables ended at virtual memory. Well, we use the same idea all over the place, and you might actually use the same idea yourself when you have to design one of these things. So we'll see that in the next class, but here, again, that's just so you have reference. So our maximum size of the file, 16 megabytes, and no one wants something like that because, you know, everyone wants to see some videos or store your games or whatever, and they're going to be in gigabytes. So we talked a little bit about file systems, and they're, again, one of the things that enable persistence. So this are the hardware part, and file systems are the software part. So they just describe how files are stored on disk, which we'll go more into detail with next lecture, but we saw some allocation strategies and ways to keep track of what blocks belong to which file today. But API-wise, we learned a little bit more. You can open files, and that actually creates a new global entry into the kernel, and then for each process just points to that global entry that has its own position. And then when you fork, both processes are going to point to the same entry, so they're going to share their position, which may mean weird things happen. And then we saw some different allocation strategies: contiguous, linked, FAT, which is the file allocation table, which was the same thing as linked, but we just store it all the pointers together. And then we saw indexed. And then we'll see some more interesting ones next lecture. So just remember, I'm pulling for you. We're all in this together.